How long has it been since we've recorded?
I think it's been 2 months. Probably 2 months. I think early June seems right to me.
Because you came home. You came home from college.
I did. From college, that's right.
You saw all your family, your little nieces and nephews.
Saw them all.
You saw me briefly.
For like 2 hours. It was nice.
And the people have been clamoring. They've been saying, when's the next episode coming out? I'm going on a road trip, and I need some reference frames to catch up on.
For that, 30-minute road trip.
For that 30-minute road trip.
I get you.
Sorry, everyone. And we also hit our 1-year anniversary of the podcast existing.
It's true. And
do you want to share your stats?
My stat? Well, I got probably like a 10 strength, maybe like a 9 dexterity.
You think you're a 10 strength?
I'm probably not. Well, I don't know. Maybe like a yeah. I mean, 10's average, like average strength.
That's true.
I think I'm average. I'm certainly clumsy, hence the dex.
I meant the podcast stats.
Oh, we have 16 episodes, and it's been about a year. And since we typically wanted to do it on a bi-weekly basis, that would be 26 in a year. So 16 out of 26, that's not exactly great. It's pretty good for a batting average though. So if
you compare us to baseball,
yeah, we're doing all right.
So here we are. We're back.
Back.
Will's gonna write his best episodes yet, since he doesn't have to teach anymore.
Oh yeah, this dissertation and that's all that's left.
It's just gonna be a writing machine. Also, are you gonna cite this as part of your dissertation?
No, I'm trying to figure out how to add this on my CV. Actually, I don't know where to put. I don't know what section this goes in. But
I've got it on LinkedIn.
Oh, that's smart.
That smart. You're a project collaborator on it. You should know that.
Well, you're also on my LinkedIn. We on our shared publication you have in the American Journal of Acoustics, or whatever it is.
You and I probably have the most links together.
I don't think that's how that works.
That's how we're linked in together.
Oh my lord! All right.
I spent a lot of time today talking about Arthurian legend, which was pretty fun.
With who?
I know. I had a coworker ask me if the Sword and the Stone and Excalibur were the same.
They're not.
That's right. But do you know what makes it so blatantly obvious they're not the same?
That he gets it from a lady in a lake and not a stone?
No.
Oh.
It's that the sword from the stone breaks.
Oh.
And Excalibur,
it
doesn't break. It's unbreakable.
That's fair. But also, they're very different ways of getting the sword.
There are. But once the legends start to go far enough back and things start to walk over themselves, right? It's hard to tell.
That's fair.
But I also learned that the scabbard is like way better than Excalibur.
Doesn't that mean you can't take damage? Like you just like immune?
Yeah.
Turns out.
And Merlin asks King Arthur, he's like, "Hey, what do you like more, the sword or the scabbard?" And Arthur's like, the sword for sure.
I can kill anyone.
Merlin has this great quote that's like, "Well, you are more foolish for thinking so, because the scabbard prevents you from ever getting hurt."
If only he had worn the scabbard all the time.
Well, yeah, but Morgan Le Fay took it and threw it in a lake.
Oh, that sounds right. That sounds like something she would do.
Yep, and that is how King Arthur met his end. Did you also know that he didn't pass the sword down?
Did he go with him to...
It was decreed that no matter how noble they were, no one else should have the power of Excalibur. So they threw it back in the lake.
What?
It went back.
That's hilarious.
Yeet.
Oh, my lord.
And you would think, like, since no one else can have it, it must be King Arthur's like last deed is to go to the lake and throw it in.
Yeah.
No, he just gave it to someone else to go throw in.
They did it? They're like, okay.
Yeah.
Well, I guess he is King Arthur. What are you gonna do? Say no?
Right.
I mean, according to Geoffrey of Monmouth, the dude like went to Rome and saw the Pope. It is very confusing.
Very confusing how he went and did all these things. Anyway, it's always fun to look up Arthurian legends.
Oh yeah.
All right. Well, here we are. What is this? Episode 17, 18?
I think it's 17.
Episode 17 of Reference Frames Podcast, the only podcast out there where we teach you physics by using our favorite media, our favorite movies and sports.
TV shows. I think we've had a TV show maybe.
Oh, yeah, we did.
Avatar. We had Avatar.
Yeah. We haven't done books because you have to imagine that yourself. Music is a little tricky as well.
It's true. Comic books, maybe. I mean, technically, Ant-Man, maybe you could argue that's a comic book.
That's true. Macaroni art has not quite made its way onto the show, but we'll see.
On the fridge of our hearts, though.
In case you're starting on episode 17, I'm Ian, and this is my co-host and best buddy, Will.
And very sweaty man. That's me.
He's very sweaty. He has no air conditioning.
Nope. It is 92 degrees outside.
That's what it's like to be a grad student. We have no corrections from our audience today from any of our previous episodes, which is very exciting, which means we can move directly into the theater of mind.
Yeehaw! 5 men line up against a wall with height demarcations and squint up at the bright lights above. A strange collection of characters sporting vastly different clothing, hairstyles, and speech patterns, they read a short phrase off of a note card passed from one to the other. One of them clearly has a penchant for the dramatic arts and is quickly told to shut it by the police officers viewing them from a dark room. The 5 men were called in following a truck hijacking, and their attitudes suggest this is a regular occurrence, more akin to a nuisance. This scene begins 6 weeks after the opening scene of the film, setting off the events that led to a ship being set on fire in LA Harbor, killing 27 people and injuring 2. One survivor serves as the narrator for the story, explaining how that very police lineup led to the 5 men deciding to pull off a heist to get back at the police. They end up robbing a smuggler of millions in emeralds, and getting the more than 50 corrupt policemen escorting the smuggler arrested after leaking their activities to the press. Now, how this robbery leads ultimately to a burning ship in San Pedro Bay is a much longer tale, filled with twists and turns aplenty. Alright, Ian, do you know this movie, Ian? I didn't describe a ton about the plot, so I don't know if you picked up the film.
You didn't. My gut reaction is the usual suspects.
That is it. Good gut.
All right.
Very good.
Kaiser Soze.
Kaiser Soze. Have you seen that movie?
Once a while back, yeah.
Yeah, it's a good one.
I enjoyed it.
It's hard to enjoy Kevin Spacey movies nowadays, which is unfortunate.
Unfortunately so, yes.
But back in the day, before we knew all the, less than great things, great film.
Yeah, agreed. That's when I saw it as well, and I probably won't go back and watch it.
Yeah. So what are we talking about today?
Boy,
Ian?
you didn't even do any physics in here.
Oh yeah, maybe I did, maybe I didn't. Who's to say?
Okay, so let's see here. Oh, you know what? I think I know. I'm honing in. My brain is... My LASIK alerts are going on.
Oh boy, here we go. What did your LASIK give you?
I'm remembering when you discussed people squinting into lights. Police in a dark room. I think, if I'm not mistaken, we're going to discuss eyeballs as cameras, maybe.
Ooh.
Or cameras in general. I think that would be a cool topic, getting into biophysics.
Okay.
Or maybe it's a mislead and you've led me astray once more. And you're going to talk about boats instead.
Or talking about boats? No. So you were actually right on the money up until you guessed what it was. We were not talking about eyeballs, though I'll write that down as a potential future topic because I did interesting.
Thank you.
No, we are talking about mirrors / reflections / specifically one-way mirrors, as you see in interrogation rooms, where inside the room, all you see is a mirror, but outside the room, looking in, you can see what's going on. It's like a window from one side. Talk about how that
works. This is a very
works.
focused episode.
Yeah, well, we'll talk about reflections and light bouncing off stuff in general too. But
cool, I'm excited.
Yeah, it's fun stuff. All right, so kind of backing up a bit, working our way towards what mirrors are. So there's one thing you need to know is that whenever light hits a surface, interacts with the surface, 3 things always take place. Some of the light is going to be reflected, so it's going to bounce backwards. Some of the light is going to pass through that surface, and some of the light is going to be absorbed in that surface, usually dissipating as some sort of heat or heating up the surface as it hits it. And it's worth pointing out, depending on what the surface is or what it's made of, some colors of light may do these different things in different proportions. So green light might be reflected, while red light might be transmitted, that kind of thing. All right, so that's the basic overview of what light does when it hits something, pretty much anything. Cool with that so far, Ian?
Yeah, let me recap. Yeah. It either reflects,
bounces off,
it goes through, or it gets absorbed, generally in turning into like heat, heating up the surface.
Exactly.
Yeah.
Exactly. Cool.
Yep.
And we're going to mainly focus on the transmitting, so going through, and the bouncing back, which is reflecting. All right. So for very smooth surfaces, right, the light that will bounce off of it will typically bounce back in the same angle it came in from. So you can imagine taking a ball and bouncing off the floor, right? It goes out at one angle, bounces off at the same angle, but in the opposite direction, right? That's what happens on a very smooth surface. The light will kind of bounce off smoothly. And this is what we refer to as a reflective or mirror-like surface. So anything that you can see, any kind of glossy surface is where it's a very smooth surface where light can just bounce off like a ball on a floor. Most surfaces, though, aren't that smooth. So you imagine like, a rough surface, sandpaper, something like that. In that case, when the light hits it, it'll bounce off at a bunch of different angles, depending on where it hits that surface. And this is what we refer to as there being no real quote-unquote reflection. There's no outgoing single direction that the light bounces off in. Cool with that so far? So basically, rough surfaces, smooth surfaces. That's the distinction between a shiny surface, a reflective surface, and a non-reflective surface. That make sense to you?
Yeah.
Cool.
I think so.
Cool.
Is it kind of why maybe on a car that's glossy, you can sort of see a reflection when it's been freshly waxed versus a car with a matte paint job, which is rougher and you see no reflections.
Exactly.
Okay. Got it.
All right, cool. So let's talk about how we make a mirror, because we're ultimately focusing on mirrors, right? So the typical procedure for manufacturing a mirror is you have some piece of glass, a very, smooth piece of glass. That's important. Which then you put on a very thin layer of metal, usually silver, but it could be any sort of reflective material. Typically metals are used. And you kind of coat the back of that piece of glass with that metal, a very thin layer, and then you put like a typically black backing on it. Sometimes green, but whatever. Some darker color on the back of that metal. There's a few reasons we do that. The reason we use glass, one of the reasons we use glass is that it's very flat. You can make it very flat, so the layer will therefore be flat on the back of it. And like we said, flat surfaces make more reflective surfaces. But also it reduces the cost, because if you had just a big sheet of silver, that's more expensive, right? Because silver is more expensive than glass. But also silver tarnishes easily if it's exposed to the air. It'll get non-reflective quickly because the surface will oxidize, and eventually it won't be reflective at all. So the glass serves to protect it from the air, and it also protects it from being scratched or damaged, right? So basically, that's the basic idea of how we make a mirror. And as you can imagine, the idea is the light goes through the glass because it's clear, bounces off the metal, and because it's flat, it bounces off neatly, makes a nice reflection. Does that make sense?
Yeah,
Cool.
Makes sense.
Cool.
So far, so good.
So because it's a little bit more complicated because of the glass, we're going to simplify things because we're physicists here. Let's just imagine that we only have the thin sheet of silver with the black backing as the mirror. We're going to ignore that layer of glass because it doesn't affect much, but there's a lot of like slight nuances that'll sort of matter. But we're going to just ignore those because they're not the most important parts here. All right?
We're not engineers.
Exactly.
Well, technically I am, but
I'm definitely not an engineer. That's my dad. So for this discussion, imagine a mirror as just being a black, maybe fabric, obviously very stiff black fabric with a thin layer of metal on it, typically silver. Okay? So you might ask, why do we need the black backing? What's the point of that? Like the silver reflects the light anyway. But remember, at the beginning, we talked about what light does. It always, some of it will bounce back like we want, but some of it will go through. And so we don't want to have a see-through mirror, even if it's slightly see-through. So we put the black backing on because that'll absorb most of that light. Because remember, the third thing a surface can do is absorb it. And black is a very absorbent color. So basically, if the light manages to make it through the silver, it'll just get absorbed by the black backing or dark backing. Does that make sense?
Yeah.
Cool. Mm-hmm. Okay, so we're talking about this light going through this metal surface, right? That might seem unrealistic. We have metal that isn't see-through all around us, right? For reference, not a lot of light is typically transmitted through a thin sheet of metal. So as an example, if you look it up, if you have a sheet of aluminum, so a different metal but same idea, that is only 10 nanometers thick, which is not very thick. For reference, if you do some very quick calculations, 10 nanometers is roughly 40 atoms thick, so not very thick layer of aluminum. Roughly only 15% of the light will pass through it. So not a lot. A decent amount, but not a lot. Most of it, 70% of it, will be reflected. The remaining 15 being absorbed. So the vast majority of the light will still reflect off, even that thin of a layer, but some of it will get through, right? And that is the interesting part when we get to what we're seeing in this scene, all right? And worth pointing out, that's at 10 nanometers. If you just triple that to 30, basically all light is reflected. So it's very thickness dependent. If you make it even thinner, more lights make it through. Make it thicker, basically no light gets through.
Sure.
Does that make sense? Cool. Okay, so that's great, Will. We talked about mirrors. That's awesome. How do these one-way mirrors work? How does light only go through one way and not go through the other way? Because nothing you talked about seems like it would suggest that can happen. Well...
yeah, riddle me that, boy wonder.
Riddle me that, boy wonder. Well, the answer is there is no such thing as a one-way mirror. Light, there's no material, there's no surface where light can only pass through in one direction. Instead, what they're basically making is just a mirror but without that black backing. So light can go through. Now you might ask, okay, so why isn't it just a two-way mirror or a no-way mirror or whatever? Like, why isn't it just a mirror then on both sides?
Yeah.
So, good question.
Why isn't the silver on the other side of the mirror too?
Yeah, hold your phone, all right?
Okay.
Anyway. All right, so let's go with that 10 nanometers because those numbers are kind of convenient. 70% transmission, 15% reflection. Right, we'll go with these broad ballpark numbers. They aren't accurate for most mirrors, but if you want to make a two-way mirror, you make it very thin on purpose. So the trick, the reason that I emphasized in the scene, and the reason you see this in the movies is it works as long as one room on one side of the thing is very brightly lit, and the room on the other side, in this case the observation room, is very dimly lit. And we'll talk about why that matters in a bit. Okay, follow me so far, Ian?
Okay. Yeah. Well, you haven't told me why,
I know,
but I
but
understand
the setup,
that one room must be bright, one must be dark.
Cool. Let's talk about why.
Yes, just what I was wanted.
Yeah. So let's say we have this interrogation room in this scene. All right, these 5 guys are lined up. They're squinting under the light. It's very, very bright. One of them even like hides his face, his eyes under his hand. Let's say that room has some amount of ambient light in it from these lights up above. And let's just say there's 10,000 units of brightness, whatever units we care about, right? It's 10,000 brightnesses, all right?
Okay.
If we therefore have this mirror that is 10 nanometers thick of aluminum, 15% of that light, those light units will pass through. So roughly 1,500 units will go through. 10,000 beginning, 7,000 will bounce back, 1,500 will go through. All right? Follow me so far? Mm-hmm. That's the whole transmission reflection stuff.
Yeah.
So let's just say that the observation room is much less bright. So it's 10,000 in the interrogation room. Let's say it's just 1,000. So a 10-fold decrease in the room where people are sitting and watching these people in the lineup. All right?
All right.
So like we said, the light that's coming in from the interrogation room is about 1,500 units worth of light, right? 15% of the original 10,000. In that room, that ambient light we said is 1,000. 70% of which is going to bounce back, right? The whole 70% reflection. So the amount of light that they get from their own, that their own reflections are bouncing back with, is only about 700 units, 70% of 1,000, right? So the light coming in from the interrogation room is 1,500. The light from their own room bouncing back at them is only 700. So it's more than twice as bright, the light coming in through the mirror, transmitting, than what they have in their room. Mm-hmm. So therefore, the light that they see, the scene going on in that room, will be more than twice as bright as their own reflections are in the mirror. And that's where they're able to see what's going on there. Does that make sense? So that kind of explains how they're able to see what's going on in the interrogation room. You kind of see what?
Yeah.
Cool.
Yeah, I think that makes sense.
So why is it then, to the interrogation people, the people lined up, that why can't they see, right? Like, why doesn't it go both ways? Well, it is. There is light coming through from the other side, but let's do the numbers again, right? So of that 1,000, so in the dim room, there's 1,000 units, a tenth of the 10,000 in the interrogation room. Only 15% of them, so only 150 units are getting through, right? They have 1,000, 15%, 150 units of light coming back at them, coming through the thing to the interrogation room, all right?
Yep, right.
Meanwhile, they have 10,000 units in there, 7,000 which are bouncing back because 70% reflection, right? So if you compare those numbers, their reflections is 7,000 units, and the transmitted from the observation room is only 150. So it is entirely washed out. Like, there technically is an image that is there, but it is so washed out by their own reflections, because it's, 50 times brighter? So, like, they're not going to see the people in the observation room.
Right. Yeah.
So what's actually going on is light is going both ways. It's just because of proportions, and if you have a dim room and a bright room, the bright room can be seen both ways, and the dim room can't. Does that make sense?
Yeah, that makes sense to me.
Isn't that cool?
It's pretty dang cool.
So where do we see this kind of thing going on? And it's worth pointing out, if you were in that interrogation room and you shut off the lights, and then you shone a flashlight into the observation room, you would be able to see them, right? It's all about the brightness coming through the thing and from your direction, right?
Yeah.
So if you're ever wondering if you're being viewed through a one-way mirror, if you just somehow cover up the lights and shine a bright light through, maybe your phone light through, you'll be able to tell pretty quick. If you just see your own reflection, then it's not. It's a normal mirror. But if you see another room beyond it, then you know it was a one-way mirror.
How about that? Actually, in the show Brooklyn Nine-Nine, they do that a lot, where they throw off an interrogation and turn the lights on in the observation room, and you can kind of see both.
It's funny. For this episode, I considered doing the Brooklyn Nine-Nine cold open with the Backstreet Boys.
Backstreet Boys, so good.
Yeah, great. All right, so that's the idea.
Yeah.
Where do we see this kind of phenomena, or really any of this stuff we talk about, reflection, transmission? Where do you see that in the real world, Ian? What do you think? I got a few.
You ever been to Target before?
Oh, gosh, have I. Minnesota institution.
Like every single Target has like a security room. And it always, as a child, I was always like, why do they have a mirror here? And then years later, I would learn it's a security room.
I never actually realized that, but that makes sense.
Yeah. Yep. For the security personnel, I suppose.
I suppose.
That's where you could find a one-way mirror in real life.
Sure.
Also, a lot of people's sunglasses.
Say more.
Well, you ever seen those people with those aviators that are reflective? But they wouldn't be very good sunglasses if they were two-way mirrors, huh?
That's probably true. That's a good point.
What you got?
All right, so, well, the first case, I was going to say literally any mirror is just this phenomenon, right? That's stuff bouncing back.
Right.
But the two-way mirror phenomenon, you've certainly dealt with anytime you've been inside at night and you try to look out a window, right? It's really hard to see outside up until you go up to the window and like cup your fingers around your eyes and peer through.
Yeah.
Because all that light is just washing out all the light that would be coming through the window. Because windows, they're mostly transmissive. They let through almost all the light, but they reflect some of it. So if you're in a bright enough room and it's dark enough outside, all the light you see is going to be washed out by your reflection, which is why cupping your fingers around and blocking all the outside light lets you see through, because now it's not being washed out anymore.
And vice versa, if you're outside looking in,
you can see everything.
you can see everything. Right.
Yeah. Yeah. So that's sort of a similar phenomenon.
Not that anyone should be looking through, only look through the windows of your own home at night.
Please. All right, another one I have, just kind of, you brought it up earlier, right? The whole idea of a matte versus a glossy finish, right?
Yeah.
That's largely to do with just the roughness or smoothness of a surface. So the smoother the surface, light bounces off evenly. Rougher surface, it bounces off in all directions. Usually call that scattering. So you don't get a easy reflective surface out of that. Mm-hmm. Any other ones for you, Ian?
I don't want to.
And it can be beyond just one-way mirrors or
yeah, I don't want to tiptoe too much into like the various laws of reflection. Sure. I suppose
polarizers and stuff. That's fair.
Right. It's maybe a little bit of a. I don't know. Fiber optic might be a little too much of a stretch, huh?
We can talk about that later.
Total internal reflection, which is different.
It's related, but maybe a little.
But maybe
it helps. That one helps have a visual aid, and it's hard to do that in a podcast, unfortunately.
Yeah, better served somewhere else.
Yeah.
Okay, let me go back to the drawing board.
That's fine. Yeah, I have a few that are just kind of basic, easy ones you're probably overthinking. So just like the color of an object, right? Specifically ones that aren't glowing or emitting light; those are different. But any object that isn't glowing, I think it looks brown or red or green or whatever. This is that whole idea of reflecting versus transmitting versus absorbing. And specifically that idea we brought up earlier about different colors doing different things, right? So a green leaf means the green color light, that specific wavelength of light, that is being reflected. But other colors, almost every other color, is being absorbed or transmitted, but probably absorbed because, like we said, doesn't transmit very far.
Yeah.
Yeah. I have one more, but I'm not going to talk much about it because similar to total internal reflection, it's a little heavy. Because I assumed incorrectly that anti-reflective coatings you see on things, like on screens and stuff, I assumed that was like a roughness thing because that would make it less reflective, right? It's less glossy. But actually, no, it's far more complicated. Generally, it's, and I won't go super into it because we kind of talked about this sort of physics way back when on our Mirage episode.
Ooh.
We talked about like the air being easier for light to travel through if it's less dense or whatever. But the idea there is you want to have a very smoothly varying refractive index. So like the glasses have some difficulty compared to the air for light to travel through. If you make it so it very smoothly changes into the air's index of refraction, then it doesn't reflect much. But again, I only bring it up because I assumed it would be the same thing as the glossy versus matte, and it was not.
And it wasn't. I was tricked.
Nope.
Fooled.
Any others, Ian? That's what I got.
No, I think we got some good ones there. I like the car one.
Yeah. I really like the Windows at Night one. I think
Windows at Night is super good. You crushed it with Windows at Night.
Oh, thanks, pal.
got your
Appreciate
back.
ya.
Now here's a question I have. All right, let's say I set up a camera.
Okay.
So it's just looking at a plate of aluminum that's 20 nanometers thick.
Sure.
And I set up a big bright light behind it and blocked part of that light with, a recognizable shape. Let's say the letter G for good measure.
Sure.
If I just sat there and let my camera run and 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 run and
Oh,
run.
I see. Like a exposure time thing.
If I set my exposure time to infinity,
Oh boy.
I wonder how long it would take to where I would have to cut it off to get an image of the G from light transmitting through.
That's an interesting question. So you'd have to have it obviously in a very dark room, basically
Yes.
no light source at
Right.
all, and then it just shining through this 20 millimeter thick thing on the other side is only that one light. Even like that is even also blocked out, right? So you only want the one light source coming in. That's a great question. So you actually find this aluminum. I got the 10 nanometers 70-15-15 from a graph on Wikipedia of all places. If you just go to one-way mirrors, there's like a nice little diagram that shows you how the reflectivity and transmittance changes over thicknesses.
Oh, that's cool.
So referencing that, only about 5% or less of the light would be transmitting at that point. Like I said, it drops off fast. So at 10, it was 15. At 0, for some reason, I'm assuming it's like 0.001 or whatever nanometers, which is like one atom thick. It is like 90% transmission though. So, it's a very, very thin. Obviously, most light will go through because it's just one atom blocking.
Yeah, right.
But yeah, so that's a great question. 5% of the light. So depending how bright your light is, that would matter too. But the answer should be you should eventually see something through
That's
the
so
aluminum surface. Yeah.
Hey, light scientists out there listening to our podcast, let us know. Send us some pictures.
Yeah. Send us some corrections too, because I'm sure I'm oversimplifying stuff.
Cool. That was fun.
Yeah, very fun. Great question.
Thank you. You got any punchline for the physics lesson today? Or any, if viewers are going to take away one thing to remember, what is it?
I think, if you're in a shady hotel and you're like not sure if that mirror is a real mirror or not, just turn the lights off and shine a flashlight on it. But also, keep these are like the classic physics thing of like, this is a thing you can see in your everyday life. You see it every night if you ever look out a window, right? So
Yeah.
it's helpful to remember that like these aren't esoteric things. Like physics generally is how the real world works, right? Sometimes it gets a little crazy with like quantum mechanics and stuff like that, but a lot of physics is like explaining everyday phenomena, including this one.
And that's why we love it.
That's why I love it.
Okay. Moving on.
Speaking of questions.
Speaking of
Ian.
questions, we do have some questions. Thank you all so much who have submitted questions. We were begging and pleading. We now have 5.
Woo!
If you would like to send us a question or a correction, you can do that. The best way to do it is on Twitter at Podcast Frames. You can email us, referenceframespodcast@gmail.com. But I would do the Twitter one if I were you, because then I can go on there and I can heart it and I can sort by mentions and things I've liked, and then it's easier to find them again. But today's question comes from your friend. Sorry, my computer isn't. Come here, you. There
My
we go.
friend Redacted.
From your friend Thomas Bleep,
I love Thomas Bleep. What a cool guy.
who says, "Why is it that when a droplet of rain lands on a phone screen, it looks all speckled with colors?"
Excellent question, Mr. Bleep. So he's referring to if you have like an iPhone or a Samsung or whatever, a smartphone, and you're walking outside to get some water on it. Why is it that when you look at the water droplet, it's not just clear see-through to the screen like water normally is? It's sort of like you get this crazy rainbow effect going on with this color. So there's a few things going on here. 2 of them are probably the most important ones. One is that light, that water droplet has some curvature to it, right? There's this thing called surface tension, makes the light kind of bead up into like a ball shape, right? And that shape, and this is again related to our Mirage episode. We're going to look back at Lawrence of Arabia. But that shape means that light will curve, and the curving of that light, due to that specific shape, ends up amplifying or magnifying the stuff you see underneath it. So part of what you're seeing is the pixels that make up your phone screen. We see them as little squares, right? Like maybe, I forget what the resolution is, but if it's 900 pixels wide and 2000 pixels long or whatever it is, we see just a bunch of white pixels that can turn different colors. But what's actually going on is if you look closer at it, you zoom in on it with like a magnifying glass or a water droplet, what you actually see is 3 rectangular pixels lined up inside of each pixel. We call them subpixels, and they light up 3 different colors, and that's how we make up all the different colors of the rainbow on our phone screens. So part of what you're seeing there, Thomas Bleep, is just it's zooming in and showing you these 3 colors, and depending on what color the water droplet landed on that your phone's displaying at the time, it might have in different proportions or different brightnesses. But the other thing you're seeing, it's not just zooming in on them; it's also splitting them in different proportions, right? Because that's the idea of this refraction. If you ever have a prism, Isaac Newton's pretty famous for this. If you have like a prism, it can split the light into like a rainbow, and the reason it does that is because the light travels different distances. So basically what you're seeing is a mixture of zooming in on the subpixels and then also dividing them even further because of the prism-like nature. So hope that answers your question. That's the basic idea. You're basically zooming in on your subpixels. Pretty cool.
Thanks, Thomas.
Thanks, Thomas.
So, Will, that's it. That's all we got. We've done a lesson. We've done a question.
What else is there?
What else is there even to talk about? We talked about Arthurian lore for a little bit.
Oof.
Such joy. Such fun. Folks, I hope you've enjoyed this wonderful tour into one-way mirrors.
Yeah.
This explanation of transmission, reflection, and absorption. And I hope that you, too, have absorbed at least 15% of the knowledge we shared today.
And that you transmit some of it to other people you know.
Specifically, if you like this podcast, maybe you could transmit it to your friends and family who also
all right. I was saying the knowledge. Ian's the jerk here.
Welcome to the plug zone, folks.
Well, that's good too.
Oh, that's all I got.
That's fair. One thing with that transmission joke, but also for me personally, the reason I know so many silly fun facts or interesting trivia, and I think this applies in general, not just to me, is you're much more likely to remember something and internalize it if you once you first hear it, you try and explain it to some other people, right? So that transmitting thing, it'll help you internalize and remember this kind of stuff too. That's how a lot of my things I remember. I'm like, oh, that's an interesting fact. Did you know? And I talk to like 4 people about it, and they get really annoyed at me because I'm always sharing trivia with them. But it helps me remember it as well as just spreading the knowledge. So, no joke. If you think this is interesting stuff, you should try to tell people about it because it'll help you remember it, help you think about it next time you're looking out a window at night. But also plug zone. That too.
Thank you.
You're welcome.
Well, folks, thanks for coming. We hope to hear you. I hope you hear us in the future.
It'd be nice to hear you too, I suppose.
I would love to hear you. We'll set up a voice call system. You can leave us a message.
Record yourself on Twitter.
And then send it to us. Ideally, we'll all hear another episode in another couple weeks, but it's sort of a mystery with us, so.
It's true. Well, conference season is sort of over for the next few months, so hopefully I'll be more available.
So Will's going to be writing scripts like a madman. We're going to learn everything there is to learn about physics.
Oh, yeah. All right. Nice one.
Thanks, everyone. Bye.
Bye. Bye. What an ending.